a new drug, a new kind of immunosuppressors for people who are getting heart transplants. And so he was telling me how, like, yeah, you know, they get, there's a placebo, a control group, and an experimental group, and even the doctor doesn't know who's in the placebo, who's in the control group, and who's in the experimental group, because the way the doctor acts toward the patient, that could, you know, affect. And I'm thinking, like, yeah, I know this stuff, I teach it, you know. And so perfect example. So the fact that the doctor is administering the drug, and he doesn't know if he's administering the drug to the control or the placebo. He doesn't know if he's administering the placebo or the real drug to the patient. So that is a double-blind study, because that way the way the doctor talks to the patient doesn't influence the way that the patient feels. Okay? When you have a single blind, or you're not double-blinding the study, the way that the doctor or anyone who's conducting the study, the way that they act toward the subjects can influence the subject's response. And so that can confound the study. That's why you need it to be double-blind. Is that clear? Yes?
Like with the placebo effect, can it also work like the other way? Like the doctor talks to you like, you're kind of like, they're going to give you the placebo, but they're actually giving you the real thing? Can that, like, you don't...
Like if the doctor somehow implies to you that you're getting a placebo,
yeah, but
gives it away?
Getting the real thing.
It will, because everyone's going to experience some placebo effect, probably. So that placebo part of it that you would have experienced, you're not going to. So that'll probably drop the effectiveness a little bit.
Wait, so how do you have this tester being blinded?
The tester, like the doctor?
Yeah.
So there's someone above the doctor who's supplying the pills, and they know what patient's going to what, and they send it to them. Yeah, yeah, it would have. That's pretty much the only way. Okay, so we get double blind. Why it's important. All right. Response set. We talked about, right? The surveys.
Yeah.
Social desirability bias, that's also something with surveys where you answer a certain way because you think that's socially desirable, you think that's what people want to hear. Okay, so that's also a problem with surveys. We talked about ethics. Okay, a little more on ethics. When is it okay to harm an animal?
Never.
No, it is okay.
Benefits.
When the benefits outweigh like the amount you're harming them. Obviously it's subjective, but if you can find a cure for cancer by killing a few rats, you know, hey, okay. Again, you have to debrief, right? What else? Oh, you can't. You have to like get the subject has to give you consent in order to use them in the experiment in the first place. Okay? Those are kind of the main ethics things that, like, what's it called? Debriefing is a big one that you'll probably be tested on. Yeah?
Wait, so you can't do like a blind like experiment where they don't know they're being tested and then you debrief them? Because wouldn't them knowing they're an experiment kind of mess it up a little bit?
If it is a true experiment, they're supposed to give consent. Like if it's something like naturalistic observation, that's not an experiment. Or like, remember the one on the bystander effect? That wasn't really an experiment. Like it was just, you know? Because no one's placed in a control or experimental group. So no, if it's a true experiment, you need consent. Yeah. Any questions on that? Okay. I think that's it. Yeah, that's it for chapter 2. Okay, it's still going? Okay, so we'll do chapter 3. Do you guys need a break or you want to continue?
Continue.
Continue? Okay.
I'm just going to quickly drink water.
Okay. All right, bio. My favorite. Do you guys like the bio chapter?
Not really.
Some of you? Okay. All right, so nervous system. You have the brain and spinal cord. What kind of nervous system is that? Central. Everything else is?
Peripheral.
Yep. Okay, so let's talk about the central first. So in your central nervous system, you have little things that send messages. What are they called? Neurons. Remember we built them? Okay, so go like this. Okay, the message comes in through these branches. What are they called?
Dendrites.
Dendrites, right. Then it goes to a soma or what?
Decides
Decides whether or not to send the message, whether or not to fire. Then it goes through the axon, and the axon is surrounded by myelin sheath, which does what? Insulates and speeds up. And you don't like the bio chapter.
I know.
Okay, sends it through, and then it goes to the end. Terminal buttons that have little bubbles called synaptic vesicles, which hold neurotransmitters. Okay? And then the neurotransmitters are the chemical messages that jump across the synapse and bind to the receptor sites of the next neuron, the postsynaptic neuron. Okay? Now, if your myelin sheath is deteriorated, what do you... Multiple sclerosis. Okay? So the messages get slowed down or eventually not even sent, which leads to what? Paralysis, okay, and eventually possibly even death. Now they have treatments. I mean, different people respond differently to different treatments, but it's not, you know, it's a scary disease. Questions? Okay. All right. So let me draw a neuron. Okay, so speaking of multiple sclerosis, okay, so the dendrite receives the message. The cell body decides, okay, you know, I'm going to fire. All right. At resting potential, what is the charge inside? Negative 70 millivolts. Okay, and then the actual ions. What's inside? Potassium. Even though potassium's positive, I know. Okay, overall the charge inside is still negative. And then what's on the outside? Sodium. Okay, so the cell body says, okay, let's fire. The message goes through. First, it's electric. What happens? It rushes in through the nodes of Ranvier, right? Before it was called the sodium-potassium pump. I think they call it something different now, but sodium channels. Okay, now they're just called sodium channels. So the nodes of Ranvier are sodium channels. Okay, and then what ends up happening to the charge inside? It becomes positive to about plus 30 or so. All right, and the message gets sent through, and then the neurotransmitter. So let's talk about serotonin, perhaps. Serotonin jumps out into the synapse, a bunch of them. And how do they have to fit into the lock and key perfectly into the receptor site? Like if you have a key for your door, or someone else's key, and you put it into your door, it's not going to open it, okay? Same way, serotonin has specific receptor sites, okay? Prozac and other SSRIs, okay? SSRI, selective serotonin reuptake inhibitor. Focus on reuptake inhibitor. Normally what happens after is, goes back in, okay? Whatever's left over goes back in. If you're preventing the reuptake, then it stays in the synapse, and what keeps happening? Keeps firing. So you have higher serotonin activity in your brain. Okay, people who suffer from depression tend to have low levels of serotonin, so SSRIs increase the level that way. Is that clear? Okay. Remember how complicated it seemed in the beginning?
Yeah.
So it's easier now?
Yeah.
Good. Yes?
Is serotonin arousal or dopamine?
Serotonin's just like a mood regulator one. Dopamine is like the happy one. Yeah, you would think that depression would be linked to dopamine, but serotonin's the one that it's more linked to. Dopamine is more linked to drugs and schizophrenia. Okay? And low levels would be linked to Parkinson's. Okay? Which we'll go over in a second. Okay, what do you call the helper cells? Glia. Good. Just like an avocado. Still recording? I'm impressed with this iPad. Okay. So we remember, just like the toilet example, after the neuron fires, what happens?
It can't fire.
It can't fire. There's a refractory period, like a gun. Okay? All right. So there's a refractory period, and it's literally like a split second, and then it can fire again, okay? Again, all or none principle, it either flushes or it doesn't, or fires or it doesn't, or stuff, okay. Okay, this is all the stuff we just covered. Yeah, you guys know this. Okay. So, disorders associated with, well, actually we'll get onto these in the individual slides. Okay, so first is acetylcholine, or ACH. Has to do with movement and also memory and arousal. And so with movement, this is the one where snake venom will act as an antagonist. So an antagonist, remember, like fits into the lock and key perfectly, and it blocks the real thing from getting through. So with snake venom, it fits into your acetylcholine parking spot. So can acetylcholine then get into the parking spot? No. So then you're missing acetylcholine, which prevents you from moving, which results in paralysis. Okay. Another thing is low levels of acetylcholine are linked to Alzheimer's. So remember, A in Alzheimer's and A in acetylcholine. And it is a memory one, and Alzheimer's has to do with memory. Okay? Botox works in a similar way as snake venom. Do you want me to, can I move on, or are you guys writing?
Yeah.
Move on? All right, the next one is dopamine. This is a big one. Dopamine and drugs, right? Drugs like Coke raise your levels of dopamine. Dopamine is the feel-good neurotransmitter. Over time, if you keep raising your levels of dopamine, your body's going to think like, okay, you know, it doesn't need to make enough. So then if you try and get off the drugs, what's going to happen? Yeah, you're dependent for basically kind of like your happiness, right? So that's that. They've also found really high levels of dopamine linked to schizophrenia. So this is why schizophrenia can sometimes be drug-induced. If you're doing like really like hardcore drugs and it's messing with your levels of dopamine, it could actually induce schizophrenia. Okay, so definitely not something to mess with. Low levels of dopamine have been found to be linked with Parkinson's. And Parkinson's, because this also has to do with voluntary movement, someone who, let's say, has Parkinson's who wants to grab like a cup or something, right? They might shake, okay? And that's because their dopamine levels are very, very low, and so it's impacting their voluntary movement. So they give them a drug called L-Dopa, which basically mimics dopamine or increases your dopamine levels, okay? And what do you call a drug that mimics and increases the amount of the neurotransmitter? An agonist. So agonist versus antagonist. Antagonist, anti, right? Agonist is kind of like the protagonist of a story. Okay. Serotonin. So we talked about mood disorders like depression is linked to serotonin, selective serotonin reuptake inhibitor, you guys get that. OCD and eating disorders are also linked to serotonin. OCD, we'll learn later, a lot of it has to do with control. Like you have thoughts that keep coming into your head, and then you do something to sort of take control and relieve your anxiety. Eating disorders also have to do with control. A lot of people who have eating disorders, they have issues where they're not in control of other things in their life, and that's like the one thing that they can control. And so, you know, they might purge or they might not eat, and we'll talk about that in chapter 15, but that's another thing that's linked to control. So both related to serotonin. It's not surprising that these two are both related to the same neurotransmitter because of that. Also regulation of sleep and wakefulness, eating, possibly aggression, but this is the main stuff you need to know for serotonin. Okay? Can I move on? Yeah? Okay. Adriana? Yeah. Okay, norepinephrine and epinephrine are involved in fight or flight, okay? So fight or flight response, it's kind of easy to remember because fight and flight kind of sound similar, and norepinephrine and epinephrine sound kind of similar. So it kind of goes together in my opinion. Fight or flight is part of the autonomic nervous system, remember, because it's automatic. and we'll get into that in a second. Also linked to depression, but more so serotonin, so don't worry about that too much.